I'm going to discuss about the basic important blocks or circuits in digital systems are adders. So we simply the digital adders, we can call the digital adders or binary adders. So main thing is as why we should learn this adders. What is the importance of adders? As you know, the adders are nothing but used to perform the addition operation between a number of operands. It may be two inputs or maybe three inputs like that. Number of operands or variables. Okay. So let's see. I have given some statement C equal to A plus B. So when you are enter the statement, who is going to perform this instruction? So definitely, I would say ALU only. So my question is how to implement the ALU? What is the basic building blocks of ALU? How to construct the ALU system? So in the ALU, it has to perform that arithmetic and logical. Okay. Then come to that logical. So there are the different logical operations also there. In arithmetic, there are different arithmetic operations like addition, subtraction, multiplication, like a division, modulus, all this. Logical means this AND gate, OR gate, shifting, all this. So in this lecture, we are going to cover how to develop the addition operation in the computers. That is our intention. So addition is developed by the adder logics, adder logic. This adder logic is implemented by the adder circuits. Okay, adder circuits. So whenever we want to add any kind of data, so we are given to the adders. The adders are different types. The first one is half adder. The next one is this is half adder. Okay, HA. Next one is full adder. So these half adder and full adders only for to perform the addition on one bit. Suppose if more than one bit, so this half adder full adder is not sufficient. So we required a group of half adders or group of full adders are required. So then we call that these adders are nothing but is a parallel adders. Let time discuss half adder. What is half adder? How to implement? What is the logic for half adder? That I have explained. Half adder. So this is a combination logic circuit. So what is combination logic circuits? The present output depends on the function of present inputs only. So means if this output is changes only with respect to changes of inputs only. Let's see C equal to A plus B, as you know, right? So I have given that inputs are A value is 10, B value is something 20. What is output of C? Obviously it is a 30. So if on any one of the input, like if I change only that A value, which is 11, I will not change that B value as it is, this become 31. So always the C can be decided by the change of either A or B. Okay, so these circuits are nothing but combination logic circuits. So same way, the half adder is also combinational logic circuits. It has two inputs which are AB. AB are the inputs, and it has always two outputs. One is sum, one is carry. So why it is carry comes means because we are doing the addition on A and B. It produces two outputs, sum and carry. So we just want to be gives the truth table of a half adder. Let I denote it has two inputs A, B, and two outputs are sum, C out. So if we take the two inputs 0, 0, 0, 1, 1, 0, 1, 1. So outputs are nothing but how to get the sum, how to get the carry. So only simple is we are able to do the addition process. So when we want to do the addition of 0 plus 0, so means 0 plus 0. This 0 plus 0 means always sum is 0, carry is 0. The least significant bit, which is nothing but on the right side, is called as sum. Okay, the most significant which comes on the right side, left side, which is called as carry. So here the sum is 0 and carry is also 0. The same way we can do the next operations also. So here we can see that 0 1 addition, you know, right? 0 plus 1. So 0 plus 1 means sum is 1 and carry becomes 0. So the sum is occupied by the 1 and carry is occupied by the 0. The same way, if we can add 1 plus 0, the sum is 1, carry is 0. When you want to add plus 1 means, so this becomes 1 plus 1 is not, is a 2, right? Yes, you know, right? So how to represent two values? So 1 plus 1 is sum is 0, the carry is 1. This is equivalent of the two value in the decimal. The same way, the sum becomes 0, carry becomes 1. The sum becomes 0, carry becomes 1. After that, we are getting that what is the sum output. So, in which combination of inputs sum is true, like these two combinations. So, here I have to give you that a different. So, you know, so if you want to calculate the sum and if you want to calculate the carry, so either we can get directly from the logic gates or you may use the K-maps. So here I go for direct logic gates. Let's see if output is 1 means inputs are different. Again, when sum is 1 means inputs are different. So this is already achieved in the some logic gate in the digital logic gates. So it means it is XORing. So that's why A XOR B. That is the output of S. So that's why this S is nothing but A XOR B. And when the carry is 1, the carry becomes 1 when both inputs are 1, 1. This is also possible in the logic gates which is called as AND gate. So when two inputs are 1, output is 1 means is called as AND gate. So this is A and B. So you can write as this is called as A exclusive or B, and same A and B are given to the OR gate, AND gate, like this is AND gate, so you're getting the carry out. So after getting that expressions of sum and carry out, later you just want to be draw the logical circuit diagram. Logical circuit diagram is very important to represent your hardware in the form of gates. Okay, so here we see that uh, we have two inputs like A, B. Same inputs are given to two gates. One is XOR gate, this is called sum, and this remaining output is AND gate. The remaining is given to that given to the AND gate. So this can produce that output is C out. So sum is this A and B are given to the XOR gate. XOR will give that sum output A XOR B. And carry out means the same inputs A and B can be driven to the AND gate. It will produce that R out. So you can check any random case. Suppose if I pass that different combination of inputs, so I have to check with one combination whether the circuit diagram is work properly or not. If I give 1 1, okay, so this 1 1 is a drive to the XOR gate as well as AND gate. So whenever the OR gate, XOR gate will take the two inputs are 1 1. So 1 XOR 1. So both are same. So the output is 0. So when the same 1 1s are going to that AND gate, the output is also 1. So as you expected, sum is 0 and carry is 1. That's why this logical diagram is working fine with respect to that verification of the logical diagram. Same way, you can implement that full adder also. So full adder is nothing but is a same combination logic circuits, but it can add up to three inputs. Half adder only can limit up to two inputs, but full adder can add up to three inputs. So the three inputs are given as A, B, and the other input is C in. So it can produce always two outputs, sum and C out. That is the standard rule for any adder. Okay, sum and carry out. Sum is nothing but least significant bit. Carry out is the most significant bit. So it can add A plus B plus C in. So we have three inputs are there. So there are total we have eight possible combinations are there. So we can list out all these inputs along with that combination of data. Let's see. Okay, this is AB. Let I give that 0 0. So carry, you always better to write a C out first and S is later, because of carry is MSB and sum is LSB. This depends while doing addition. So combinations are 0 0, 0 0 1, 0 1 0, and next one is 0 1 1 and 1 double 0, 1 0 1, 1 1 0, triple 1. Okay. So when you want to add a 0 plus 0 plus 0, so sub is 0, carry is also 0. So when you want 0 plus 1, if the sum is 1, carry is 0. If you want a 0 plus 1 plus 0, sum is 1, carry is 0. If you want to add 0, 1 plus 1, this becomes 2. So carry is 1 and sum is 0. When you want to add 1 double 0, the sum is 1, carry is 0. So when you want to add 1 plus 1, the sum is 1 or sum is 0. Sum is 0, carry is 1. When you want to add 1 1 0, sum carry is 1 and sum is 0. When you want to add plus 1 plus 1, 3. 3, how to represent 3 value? In the binary pattern, 1 1. So this is the way you can get the sum. So out of 8 combinations, so only few combination only S becomes 1. So we can find out, we can get what is the expression for sum, what is the expression for carry. So all this will get it. Okay. So this is the logic we need to get when we are implementing the sum. I can directly get by using either by using k-maps or by the logic. This logic is the sum expression you can get from the by using k-maps. It is AXR, BXR, Cn. Okay. The carry out is so A, B, C, AB plus BCN plus ACN. This is nothing but AND gate logic between the two gates. This is nothing but so full adder logical expressions. So once we have confirmed with that, what is that sum, what is carry out, we can draw the logical diagram. The logical diagram is very, very important. So first of all, you can take the two XOR gates. The first XOR gate will take ABR inputs and it will take the same as second XOR gate. This is some Cn. At the same time, you are also getting that second output. The second output is also very, very important. So when you see the second output, the carry is the second output, right? So here, how to get the carry? So the carry is nothing but so A and B are given to that AND gate. So take one more AND gate, take one more AND gate. This is nothing but B and C. And you can directly get from the signals, or you can give directly the values A and C. So these three are given to the OR gate. So to the three input OR gate, it is gives that C out. So this is nothing but A XOR B whole XOR Cn. The carry is nothing but AB plus BCn plus ACn. So thank you for everyone. So this is the today's class. We will see remaining concepts in the next classes. Thank you.